I'm Donna Nelson, and I'm going to continue my lectures in organic chemistry in this video. And we're going to cover Chapter 17 out of Klein's textbook, Aromatic Compounds. And so, in this first video, we'll look at the introduction to aromatic compounds, the nomenclature of benzene derivatives, structure of benzene, and stability of benzene. And then in the next lecture, which is videotaped, we'll look at the reactions of benzene and some other aromatic compounds as well. So let's get started. So benzene, these aromatic compounds are often called arenes. You can see that benzene has three pi bonds, which are conjugated. Toluene and the xylenes are also aromatic compounds. They're all called arenes. Even though they're called aromatic compounds, most of the aromatic compounds are relatively odorless. Aromatic rings are a common feature in drugs, as you can see. There are several examples here of drugs, and they have several aromatic rings in them. And we will look at each of these so that you will be able to see how these rings are indeed aromatic. Coal contains aromatic rings fused together and joined by non-aromatic functional groups. So the parts in green are non-aromatic, the parts in yellow are aromatic. And so, let's see, the nomenclature. Benzene is the parent name, except in cases where you have a long chain which has greater than 6 carbon atoms. So this is chlorobenzene, nitrobenzene, ethylbenzene. And so these benzene derivatives have common names which have been accepted and adopted by IUPAC. And so these can be used as the parent name. And so methylbenzene is called toluene, hydroxybenzene is phenol, methoxybenzene is anisole, aminobenzene is aniline, etc., etc., etc. And so it will be necessary for you to learn the names of the compounds shown here. If the substituent is larger than the ring, so this is 1, 2, 3, 4, 5, 6, 7 carbons, so this is 1-phenylheptane. Benzene rings are sometimes abbreviated just PH, meaning phenyl, or they can use the symbol, the phi, Greek letter. The common name for dimethylbenzene is xylene. So there's orthoxylene, metaxylene, and paraxylene. And it will be necessary to learn this nomenclature. So 1,2-dimethylbenzene is called orthoxylene, and it's said that one methyl is ortho to the other, or you might hear it said that the methyl is in the ortho position, or that the two methyls are ortho to each other. Similarly, this 1,3 substitution pattern is called meta. Similarly, these two methyls would be said to be meta to each other. This methyl is in the meta position respective to the other methyl. And the 1,4 substitution is said to be para-xylene. So these two methyls would be said to be para to each other, or this methyl is para to the other methyl, or in the para position. So this is orthonitroanisole. So here the nitro is ortho to the methoxy group. This is the parent name. The anisole is the parent name. You could also name it 2-nitroanisole, or here meta-bromotoluene. So bromo is said to be meta to the methyl group of the toluene molecule. This is 3-bromotoluene. This would be parachlorobenzaldehyde. So benzaldehyde is the parent molecule. So this is chloro is in the 4 position relative to the aldehyde functionality. So parachlorobenzaldehyde. The nomenclature of benzene derivatives is in several steps. First, you identify the parent, identify and name the substituents, number the parent chain, and assign a locant, a number, to each substituent. Give the first substituent the lowest number possible. List the numbered substituents before the parent name in alphabetical order. Ignore prefixes like di or tri, except you do not ignore iso. And remember that in sec-butyl or tert-butyl, the sec and tert are italicized, but in isobutyl, the iso is not italicized. So identify the parent chain. Here the parent is phenol, and you have the 2 bromo functionalities, so you identify and name the substituents. So this is going to be dibromophenol, and you have to specify which positions they're in. So you start numbering at the functional group that is in the parent compound. So we start numbering at the hydroxyl substituent because it's part of the part of the parent compound. So it is always, by definition, at position 1, and then you have the 2 bromo functionalities, which are in positions 3 and 5. So this is 3,5-dibromophenol. 1, 2, 3, 4, 5. 3,5-dibromophenol. So Kekule was the first to propose that a benzene ring is composed of alternating double and single bonds. And you can see here, you can see the double bond, single bond, double bond, single bond, double bond. And over here, you can see that the double bonds have moved so that they are in different positions. He suggested that this was an equilibrium process. And initially, the chemical community believed it was indeed an equilibrium. They knew that it could either be an equilibrium or that the 2 compounds could actually be in resonance with each other. So the 2 compounds, the actual structure of the molecule, there would be one structure that was somewhere in between these 2 structures. So there's a difference there between alternating between 2 distinct structures versus having one structure that is in between these 2 structures that are drawn. And so the chemical community initially thought that it was an equilibrium. And so what the chemical community initially said is that the 2 structures were in equilibrium, and these were 2 distinct structures. And at that time, they were saying that the these two structures resonated, in other words, jumped back and forth between the two structures. And it turned out that was wrong. When it was proved wrong, the chemical community had a meeting to discuss, well, how do we talk about these now? Because we've spent all of this time, and it's in the literature, saying that these two structures resonate between these two structures. They're two distinct structures going back and forth, sort of vibrating back and forth between the two different positions. And they said, how are we going to discuss these now, now that we know that this is wrong? And so it was decided at that time that that the chemists would never speak again about these two structures resonating. They would always say that the two structures have resonance. And so if you look through the textbook, you will never see it stated that the two compounds are resonating. In other words, jumping back and forth between the two structures. You will see it said that these two structures have resonance. So the actual true structure of that molecule is in between these two. So the pi system is sort of like a blur, where the pi system is not isolated here and then it jumps over here and they jump to these these new positions. The pi system stays in one place and it has resonance. So sometimes the pi system is drawn, it's just indicated by a ring because there's a continuous flow of electron density all the way around the ring. And this arrow indicates resonance. This double-headed arrow indicates that these two molecules are in resonance with each other. They have resonance. Benzene has resonance. You never say that benzene is resonating. Resonating can mean like to vibrate, like the reed of a saxophone. That explains the terminology. So you would never want to say that benzene is resonating between the two structures. Aromatic rings are remarkably stable. Recall, alkenes undergo addition. Here is the addition of bromine across the double bond. Aromatic rings do not undergo reactions like this. The double bond is tied up in conjugation with the other pi bonds, and they're stabilized by aromaticity. And that makes this ring very stable, too stable to undergo reaction with bromine in most situations. Occasionally you can put substituents on here so that it will react, but just benzene without any substituents will not react. So how stable is the benzene? Here is the benzene. If it is hydrogenated, energy is given off. So if this is hydrogenated to give cyclohexane, energy is given off and observed how much is given off. So only 208 kilojoules is given off to bring this molecule down to the level of cyclohexane. So this, once it's determined, can be compared with cyclohexene, and that can be hydrogenated to give the same product, cyclohexane. And so one double bond, which is an isolated double bond, obviously, gives off 120 kilojoules when it is hydrogenated. If you have two double bonds in conjugation with each other, 232 kilojoules are given off when this is hydrogenated to give the same product. So one isolated double bond is worth 120. Two conjugated double bonds are worth 232. And so this is a theoretical molecule. This has not been synthesized. It does not exist. And so its expected energy that would be given off could be calculated to be 360 kilojoules. That number is taken by tripling this 120. 3 times 120 is 360. And so that is what would be expected from 3 isolated carbon-carbon double bonds. So the aromaticity then is the difference between this 208 and 360. Additional 152 kilojoules per mole of stabilization is what the benzene has due to its aromaticity. Here are some orbital representations of benzene, and you can see the 6 pi orbitals of benzene. 3 of these are bonding, 3 are anti-bonding. Remember, benzene typically contains 6 pi electrons. These are only the pi orbitals. You can see here there's 2, 4, 6 pi electrons occupying the 3 lowest energy molecular orbitals, and so these are the bonding MOs. These have energies of stabilization. Up here, these have energies such that if one of these is populated, it will destabilize the molecule. And so you can see these 3 will be populated. Psi1, the lowest energy bonding MO, molecular orbital, has no nodes. Psi2 has 1 node. It is at the same energy level as Psi2 prime, which also has 1 node, and you can't really see it. It's here in between the blue and the red. So these 2 are at the same energy level and have the same number of nodes. 0 nodes, 1 node, 2 nodes, 3 nodes. The number of nodes increases as the energy increases. Now over here, this is a molecular orbital, but it's an approximation made up of 6 atomic orbitals. So these are the atomic orbitals which are taken together to create 1 molecular orbital. This is the atomic orbital representation for Psi1. Notice that all of the red lobes are on top and all of the blue lobes are on bottom. Just like here, the red is on top, the blue is on bottom, and so here you will have overlap between all of the red lobes, all of the top lobes. Electron density will circulate through those, and when they do circulate, this is the molecular orbital that is formed. So this is the atomic orbital drawing for Psi1. This is the actual molecular orbital. This is the drawing of the molecular orbital. So they represent the same thing, but they represent it in different ways. So, don't get confused. Atomic orbitals, molecular orbitals. Now, you can also have compounds which are anti-aromatic. And so those will be compounds that do not have 6 pi electrons. And you can have compounds that are non-aromatic as well. Sometimes these this can be confusing. So this is a cyclic molecule, just like this one, and you do have the pi bonds in conjugation with each other. The p orbitals are overlapping. Here you can see these are overlapping, but they do not have an odd number of electron pairs. So think about it. Benzene has 6 pi electrons, and so that's an odd number of pairs. So it has 3 pairs of electrons. So that is what makes it aromatic. This has 2 pairs of electrons. 2 is not an odd number. This is not aromatic. This has 4 pairs of electrons. This is 4 is not an odd number, so this compound is not aromatic. And so this cyclooctatetraene can react with bromine because it is not aromatic. It is not giving up any aromaticity when it reacts. And so that's the difference between aromatic and non-aromatic compound. These representations are showing the fact that if you reorganize these pairs of electrons, you can reorganize them in ways to get 2 molecules of cyclobutadiene, which is another anti-aromatic compound. Aromatic compounds must meet 2 criteria: a fully conjugated ring with overlapping p orbitals. And so, for example, if you just have a linear ring, an acyclic pi system, such as hexatriene, that's not cyclic. So it would not fulfill the first criterion. So here we've been talking about cyclic systems. I've just discussed with you on the previous transparency how cyclobutadiene and cyclooctatetraene do not have an odd number of electron pairs. And so these would not be expected to be aromatic. So if you look at the MOs, the molecular orbitals, Psi1, Psi2, and Psi3 of cyclobutadiene, so you can see the 2 pairs of electrons, 4 electrons, and so 2 would go into Psi1, 1 into each of Psi2 and Psi3 because these are at the same energy level. And so that also explains the lack of stability. It does not have a closed shell electron configuration because you don't have pairs of electrons. So that is part of the reason why it is anti-aromatic and unstable. A similar analysis can be made for cyclooctatetraene. Here you can see the 8 electrons, and when you put them into the molecular orbitals for cyclooctatetraene, you can see you have 2, 4, 6 go into bonding orbitals, and 1, 2 are unpaired and occupying 2 non-bonding molecular orbitals. So this compound is not expected to be stable. Indeed, it's anti-aromatic. It adopts an unusual sort of tub-shaped conformation so that it can avoid some of the overlap. Notice now the p orbitals are no longer fully overlapping with each other, and that way it avoids some of the interaction so that it, since it's not planar, it avoids being anti-aromatic because the p orbitals are not fully overlapping. So, that ends the first lecture for aromatic compounds. And in the next lecture, we will go on to look more at aromatic compounds and some of their reactions.